A single subatomic particle is just 0.1% heavier than it should be, and that tiny error might just break physics as we know it. For decades, the Standard Model has perfectly explained our universe. But deep inside 4 million recorded collisions, something impossible was hiding. To understand why this microscopic anomaly is causing a massive earthquake in science, we need to go back to the beginning. I have to speak openly. Preparing this video was pretty difficult. Because when following certain developments in physics, some topics remain highly technical. First, understanding the technical side of the subject, then structuring it in a way we can all understand. And explaining it is truly hard. The topic we'll discuss today is one of the most technical we might encounter, but its implications are massive. That's why I tried my best to grasp the concept, then put it together and sat in front of the camera to tell you about it. So here is what happened. Physicists discovered that the carrier of the weak interaction, one of the 4 fundamental forces, or the weak nuclear force, known as the W boson, is 0.1% heavier than the Standard Model predicted? You might think, so what? But if this is true, if it gets confirmed, it could mean the Standard Model as we know it has to be rewritten. And that means rewriting physics entirely. This finding, that the W boson is heavier than predicted, is still very new. It was published in the journal Science earlier this month. And it wasn't even from a targeted study. It was an anomaly found while analyzing data from a particle accelerator that doesn't even run anymore. The accelerator we're talking about is the Tevatron, located at the Fermilab laboratory. The Tevatron last ran 10 years ago, leaving behind years of archived data. Researchers working at Fermilab constantly analyze this data. The W boson was just one of the particles they were examining. And finally, from deep within this data, the Y boson delivered a massive surprise. We will get into the details of this surprise, but in short, this finding tells us this. If this discovery is confirmed, it could point to undiscovered particles and even new forces we can't see in the universe. This could cause the laws of quantum mechanics, which haven't seen a new vision in a very long time, to undergo a massive transformation once again. Theoretical physicist Stephen Helnwein says this about the situation. Theoretical physicist Stephen Helnwein says this about the situation. It could completely change our understanding of the universe. This W boson finding could even overshadow the Higgs discovery in 2012 because the Higgs matched previous predictions. This could open up a completely undiscovered new frontier for us. So as you can see, the situation is serious. Here's the thing, we kinda know the Standard Model. We've talked about it a few times. With its countless equations containing all the particles and forces we know, looking like a terrifying labyrinth of ink, it's actually a model housing all the equations and laws we understand. And this model works almost flawlessly. We say almost because as far as we know, the Standard Model, this Standard Model we trust so much, is incomplete. Yes, our most successful model is missing pieces. That's exactly why, for a very long time, the biggest dream of physicists has been to find these gaps and even rewrite the Standard Model entirely. And this finding might just have offered that exact opportunity. Let's understand the W boson first. W bosons, as we mentioned, are the carrier particles for one of the four fundamental forces of the universe, the weak nuclear force. The other forces are gravity, electromagnetism, and the strong nuclear force. Unlike features like pushing or pulling, the weak force generally does the job of turning heavy particles into lighter ones. For instance, a neutron decays to become a W boson and a neutrino. And then this W boson turns into an electron and another neutrino. The importance of this is, during this process, as a result of this subatomic transformation, radioactivity is produced. And in its simplest form, our sun gets its energy from this very process. So, without the W boson, you wouldn't be sitting here right now. In many experiments, the masses of W bosons have been measured for the last 40 years. While this process is relatively easy for other particles, this transformational nature of the W boson makes calculating its mass exactly quite difficult. Still, by factoring in its connections with other particles in W boson studies, they could actually predict the existence of new particles. This is crucial. Thanks to this, before the top quark was discovered in the 90s, and before the Higgs boson in the 2000s, their masses were predicted incredibly closely. But the warp boson itself is not an easy target. In the study we mentioned earlier, from the Tevatron Particle Accelerator's runs between 2002 and 2011, around 4 million recorded W bosons were examined. The reason this study took nearly 10 years was the incredible uncertainty they faced in the data. And of course, they had to verify their findings over and over again. According to the Standard Model, the mass of the W boson is predicted to be 80,357 mega-electron volts, with a margin of error of plus or minus 6. We are talking about incredibly precise measurements here. But after their study concluded, and following countless reanalyses, the new measurement revealed the WO boson's mass to be 80,433 mega-electron volts, with a margin of error of plus or minus 9.4%. This means it's 77 mega-electron volts higher than what the Standard Model predicted. So basically, the fundamental math holding our universe together is off by a tiny but undeniable fraction. So what does this mean? It means a 7 sigma deviation. Let's unpack that quickly. Sigma is also known as standard deviation. To put it very simply, 4 sigma is usually a massive sign for scientists. It means there could be a new discovery deviating heavily from the standard. Anything higher absolutely indicates there's a problem with our current theory. So, a 7 sigma result naturally sent a massive earthquake through the scientific world. As we said at the start, it could mean new unknown particles, new forces, and an entirely new physics. But before we get too carried away, let's slow down, because nothing is absolutely certain just yet. First of all, the mass of the W boson has been studied many times before this. For example, In 2017, during the ATLAS experiment at CERN, a very, very tiny difference was found. But it stayed within the standard deviation, remaining a solid result. And while 7 sigma is extremely important, in these kinds of studies, it doesn't guarantee absolute certainty or a final conclusion. But it definitely tells scientists they need to reevaluate their analyses and conduct far more research. The numbers forced us to look deeper, but this opened a much bigger question. How do we fix the math? So, let's briefly look at the possible consequences of this. I mean, what could it change in physics? What kind of shift could it create? Even though the results aren't final, physicists immediately started racking their brains over possible explanations. One of these is the theory known as supersymmetry. They immediately pulled this theory down from the dusty shelves. It's come up a few times on our channel before, but we hadn't talked about it in detail. In short, by pairing the particles we know with supersymmetric partners, doubling them all, and trying to explain mysteries like dark matter, supersymmetry is, according to some physicists, the most beautiful theory poised to explain everything. But there is one problem. The Large Hadron Collider hasn't been able to find anything to support this theory. Everyone was waiting with huge hopes, but there isn't even the slightest shred of proof. Now, this anomaly in the W boson could, for some, be the sign of supersymmetry, especially since a group of physicists are still waiting for the day they will prove supersymmetry. Maybe their day has finally come. For now, with the upgrades being made at the Large Hadron Collider, it seems we have no choice but to wait for new experiments and the expansion of this study. But these possibilities, the chance for an entirely new physics, is incredibly exciting, isn't it? Humanity meeting a brand new kind of physics. There are scientists working towards this. New Max Plancks, new Einsteins, new Niels Bohrs or Heisenbergs. Knowing that someone among us, maybe a few of them, will achieve this when we meet them, even just thinking about it is beautiful. As I said at the beginning, even though it's a bit hard to understand and grasp, I hope I was able to explain why this is so important. Know that I will be following this topic very closely. And if there are any developments, I will definitely share them with you. As always, until we meet again, I'm glad you're here. Much love. Next time you look up at the night sky, remember that the invisible rules holding it all together might just be waiting to be rewritten.